Good day, everyone. Today we'll be focusing on numerical integration, which is a fundamental tool in engineering and science. This is lecture 3 for our course CE Math, Numerical Solutions to CE Problems. Now, why do we need numerical integration? Often we encounter integrals that we cannot solve analytically, either because the function is too complex or it has no closed form solution. In such cases, we approximate the integral using numerical methods. Think of it as estimating the area under a curve when exact methods fail. Throughout this lecture, we'll explore different quadrature formulas and see how composite rules improve our accuracy. Now, let's look at how quadrature formulas are derived and applied. When we talk about quadrature rules, we're basically approximating an integral by replacing the function with a polynomial approximation. This is usually based on interpolation. Here, we introduce two important terms, x sub k, which are the nodes or sample points, w sub k, which are the weights, which scale the function values. No, the idea here is simple. Instead of integrating the actual function, we integrate a polynomial that passes through selected points. In the image here, x sub k is the location of the rectangles. F of x sub k is the height of the rectangles, no? And w sub k is the width of the rectangle. Thus, the area becomes the summation of the areas of the rectangles, no, width times height, denoted in the equation here. Now, let's formalize this approximation using Newton-Cotes formulas. The nodes are assumed to be equally spaced with h, no, and k are the number of nodes present. Depending on how many nodes we use, we get different rules. The first four closed Newton-Cotes rules are the trapezoidal rule, which is a linear approximation of the function, Simpson's one-third rule, which is a quadratic approximation, the Simpson's 3/8 rule, which is a cubic approximation, and Boole's rule, which is a quartic approximation. Arranged in ascending order in terms of number of nodes, the more nodes present, the higher order the polynomial used for approximation. And we would see later that it would lead to better accuracy and also more computation. The trade-off here is that in pursuing higher accuracy, more function evaluations are needed, no? Now let's go through these formulas one by one, starting with the trapezoidal rule. The trapezoidal rule is the simplest Newton-Cotes formula. We approximate the curve between A and B with a straight line. No? Given the formula, uh, the area under the curve is approximately equal to h over 2 times the summation of the function values at A and the function value at B. No? Geometrically, this means the area under the curve is approximated as the area of the trapezoid, no? Formed by the line connecting um, f of A, which is this point, and b f of b. This is accurate, no? If the function is close to linear over the interval a to b, but can deviate significantly for highly curved functions. As you can see here, it is just a quadrilateral, no? Specifically a trapezoid, no? Hence the name. If we may recall, the area of a trapezoid is just equal to the base, which for this case is h, and the average of the two heights, no? Which are f of a, which is f of a, and f of b. If f of x, no, if the function we're estimating is exactly a straight line, what do you expect the trapezoidal rule to give? The trapezoidal rule would give the exact integral, no, with no errors. Now, let's move on to the Simpson's one-third rule, which uses parabolas instead of straight lines. Simpson's one-third rule uses a quadratic polynomial, no, denoted by p sub 2, to approximate the curve. The formula is the area under the curve is approximately equal to one-third of h times the summation of the function values at a and c plus 4 times the function value at b. No? Here, we take three equally spaced points a, b, and c. A parabola, no, is fitted through these points, no, f of a to f of b, then to f of c. And we integrate that parabola exactly. If we think about it geometrically, we're no longer approximating the curve with a straight line, but with a parabola, no, which hugs the curve more closely for this case of f of x. Now, let's dive into the derivation to give you a better appreciation and understanding for this formula. Say, for example, a second degree function f of x, no, ax squared plus bx plus c. As illustrated here, let's plot three nodes, x sub 0, x sub 1, and x sub 2. Let's place x sub 1 at the origin so that x sub 0 and x sub 2 can have their x values of the opposite sign. For x sub naught, x sub 0, that's negative h, and x sub 2, that's positive h. The distance of x sub 1 from x sub 0, no, and x sub 2 is set as the width, no, being h. Analytically, the area under the curve is denoted as the integral of f of x from x sub 0 to x sub 2, no? The Since x sub 0 and x sub 2 are end nodes, they are also our limits of integration. Because we placed x sub 1 at the origin, x sub 0 and x sub 2 are negative h and h respectively. From that, we can say that the area is the integral from negative h to h of f of x, which is ax squared plus bx plus c. Which would lead to ax cubed over 3 plus bx squared over 2 plus cx evaluated at negative h to h.